October 12th, 2025. 8 days have passed since we received the official report about the interstellar visitor, 3II Atlas, passing by our sun, leaving a trail of alien chemistry. No clear photographs, no clear answers, only a carefully packed story about a comet. But is that really the case? The gaps in this story continue to widen, and tonight we will unveil the veil of this narrative structure and ask the question that everyone thinks but no one speaks aloud. Is the official version the truth, or is something greater happening behind the scenes? Following our new multi-layered format, the revelations become increasingly grim. We will unveil the mystery of the runaway black hole, silently drifting through our galaxy, an invisible predator that could change everything we thought about cosmic safety. We will face a colossal wound, tearing the sun right now, a wound capable of disrupting much more than just our sky. Then, the final countdown. Scientists warn that the universe itself may collapse, and the time frame is much shorter than you think. And if that is not enough, the quiet but relentless rain of satellites falls to Earth every day, 1 or 2 satellites daily. The question is, why not more people are talking about this? If these mysteries intrigue you as much as they do me, don't forget to like and subscribe to stay updated as this unfolds in real time. Leave a comment on where you are listening from, what time it is, and whether you believe we are getting the full truth about these world-changing discoveries. And if you want to help this community grow, share this video on social media or just in your group chats. You are the reason we can continue pursuing such stories, so thank you for your support. Part 1. The arrival that no one can agree on. On July 1st, 2025, something arrived not from our sun, but from the depths of interstellar space, and immediately drew attention. You probably haven't heard of it. Most people haven't. But in the quiet corners of astronomical departments and research stations around the world, scientists began exchanging encrypted messages, scheduling emergency video calls, and closely examining data that refused to obey familiar laws. They called it 3I Atlas, designation in Catalog C2000. The Atlas telescope in Chile first noticed it, a faint dot moving against the stars with a trajectory telling an impossible story. This was the third confirmed interstellar object ever detected by humanity, after the famous Oumuamua in 2017 and the Borisov Comet in 2019. You may remember Oumuamua. This mysterious cigar-shaped object accelerated in a way that gravity could not explain, did not evaporate like a comet, and disappeared into the cosmic ocean before we could examine it properly. The Atlas was different, or perhaps the same. No one could reach a consensus. The reverse mathematics clearly showed one story. This object moved along a hyperbolic trajectory, meaning it was not bound to our solar system. He came from afar, from a place that is hard to imagine, and will leave again, disappearing into the abyss between the stars. His speed upon entry was about 60 kilometers per second, which is roughly 130,000 miles per hour, faster than anything humanity has ever created. Faster than solar wind. Fast enough that if backward calculations were made to trace its trajectory into the past, it would reveal that the object is heading into a part of space where no known stars could have sent it. The object will reach perihelion, its closest point to the sun, on October 30th, 2025, passing approximately 1.4 astronomical units from our star. For reference, 1 astronomical unit is the distance from Earth to the Sun, so Atlas will pass inside Mars's orbit, but remain at a safe distance from Earth's orbit. The closest approach to Earth will be about 1.8 astronomical units. Far enough that even the most paranoid among us cannot claim it, poses a collision risk. It was not melancholy. It was not, don't look up. The danger, if it existed at all, was not kinetic. But then the anomalies began to accumulate like evidence at a crime scene. First, there were size assessments. Initial calculations suggested that Atlas could be tens of kilometers wide, significantly larger than its interstellar predecessors. Other estimates sharply disagreed, proposing something much smaller, but with unusual reflective properties. The very presence of uncertainty was strange. Modern astronomy has learned to determine the sizes of cosmic objects quite accurately. When estimates vary by 10 times or more, it indicates that the surface or shape of the object misleads our instruments, which should not happen with a simple comet. Then the chemical reports arrived, and they made no sense at all. Most comets, when they heat up as they approach the sun, begin to evaporate water vapor. Water ice is the main component of comet nuclei, which sublimates into beautiful tails stretching millions of kilometers across the solar system. Atlas did not follow this scenario. Spectroscopic analysis showed that carbon dioxide dominated the emissions and water was barely noticeable. Even stranger, some observations recorded high concentrations of nickel in emissions, an element that should not appear in such quantities in natural comets. One would think that astronomers would be shouting about this on every corner. One can imagine emergency press conferences, urgent publications, telescopes around the world aimed at tracking this strange visitor. Although some of this really happened, much of the reaction was restrained and cautious, full of caveats and uncertainties. Many astronomers publicly regarded Atlas as a strange yet natural comet, an exception in distribution but not something inexplicable in its essence. They reminded that comets come in various forms. Each star system has its own chemistry. One should not expect that every visitor will match the composition of objects born in our cosmic neighborhood. However, conversations began to buzz in the comments on pre-release articles, in quiet discussions at conferences, in encrypted chats where researchers could speak more freely than in peer-reviewed journals. Some began to wonder about a question that balances on the edge of respectability in modern astronomy. What if Atlas is not entirely natural? What if we are dealing with something artificial, technological, something that was sent? The word probe began to appear, usually hidden in conditional sentences and hypothetical reflections. The word alien was spoken even more quietly, often accompanied by nervous laughter, a social signal that the speaker was aware they were treading on dangerous ground. Careers suffered from the serious perception of such proposals. Reputations were built on their dismissal, but numbers paid no attention to reputations, and chemistry did not care about careers. As October approached, when Atlas drew closer and our telescopes gathered more light from its surface, the anomalies did not resolve into convenient explanations. Rather, they multiplied. And here we are. An object from another star system is currently passing through our cosmic backyard as you listen to these words. It exhibits characteristics that don't quite fit any models of natural bodies. The data we receive is incomplete, scattered, sometimes contradictory, and the institutions we trust to understand such things speak cautiously and thoughtfully, which may be scientific caution or something entirely different. The question is not whether Atlas is strange. Everyone agrees he is strange. The question is, what kind of strangeness we mean, and who has the right to decide? In the next part, we will delve into pulsations, rotations, and the question that keeps a certain type of scholar awake at night. Is it a signal or just spinning in the void? Part 2. Pulsation in the darkness. A signal or rotation. Light tells stories if you know how to read it. Every photon reaching our telescopes carries information encoded in its wavelength, polarization, and time. When astronomers study an object like Atlas, they do not just look at a point in the sky. They analyze how the brightness of that point changes over time, constructing what is called a light curve, a graph depicting brightness over hours, days, and weeks. Most comets create chaotic and erratic curves of light. They rotate unevenly in space. Their rotation is unstable due to uneven forces caused by gas emissions. Their surface is pocked and asymmetrical. The changes in brightness we observe are essentially noise, random fluctuations that occur when different surfaces catch sunlight at various angles. This is the optical equivalent of white noise, predictable only in its unpredictability. Atlas did not quite follow this pattern, or rather, he both did and did not, which could be even more troubling. The light curve showed changes that were unusually regular, with fluctuations in brightness repeating with such periodicity that they created an impression of structured geometry rather than chaotic rotation. Some data segments exhibited periodicities that made astronomers lean closer to their monitors, double-checking their settings and wondering if they were seeing what they really thought they were seeing. The technical term is photometric periodicity, which is exactly what one can expect from a spacecraft that rotates to control its position, or from a probe designed to transmit patterns into space, or from any number of systems requiring precise angular momentum control. For the sake of justice, this could also occur from a natural object with an unusual yet explainable shape, possibly a contact binary body consisting of two lobes connected by a narrow neck, rotating in a stable configuration. But then data on polarization appeared, and everything became even stranger. Polarization measures how light waves orient as they move through space. Unpolarized light oscillates in all directions perpendicular to its path. Polarized light oscillates in specific planes and the degree and direction of polarization tell us about the properties of the surface that reflects or scatters this light. Rough surfaces depolarize light. Smooth surfaces can create strong polarization signatures. Some geometric constructions produce so-called negative polarization, where the polarization changes in the opposite direction to what you would normally expect. The atlas demonstrated extreme negative polarization at certain angles, values that exceeded what models predicted for any known natural surface compositions. One article described it as anomalous polarization behavior, incompatible with standard models of cometary dust. Another used the phrase geometric features of albedo, hinting at an elusive surface structure. These are the cautious, carefully qualified statements that scientists make when they encounter something that doesn't fit into familiar frameworks, but they are not yet ready to say what it might be. Imagine a lighthouse. A beam of light regularly scans the ocean at precise intervals, transmitting information to any observer capable of seeing. Now imagine that this lighthouse spins in space at a speed of 60 kilometers per second, reflecting sunlight in patterns that are too regular to be random, yet not regular enough to be considered definitively artificial. This is roughly what we are dealing with. It could be a signal, it might be the most awkwardly shaped stone in the universe. Data on non-gravitational accelerations added another layer of complexity to the mystery. When you precisely track the orbit of an object, you can notice slight deviations from the trajectory dictated by pure gravity. Comets constantly show such deviations. Gas release acts like a weak rocket engine, slightly diverting the comet from its course depending on where the gas escapes from the surface. In a typical comet, these forces are generally symmetrical, smoothing out over time. However, for Atlas, the non-gravitational accelerations exhibited patterns that are difficult to explain with standard gas release models. Some researchers suggested that this object is a comet with a high dust content, a dirty rock emitting mostly solid particles instead of gas, generating forces through radiation pressure on these particles rather than volatile substances. This could explain some chemical anomalies and acceleration anomalies. It was a good hypothesis, a reasonable compromise between just a strange comet and a possible alien probe. It didn't explain everything, but enough to be worthy of attention. And perhaps that was the truth. Perhaps Atlas was simply located in a poorly explored area of the parametric space of possible cometary bodies, showing us that our models need refinement, not replacement. The universe is not obligated to be understandable to us. It doesn't care if we find something confusing. She simply exists, ignoring our desire for clear categories and convenient explanations. However, this is what continued to trouble the researchers studying these light curves late into the night. If you wanted to send a probe to another star system, designed to be detectable yet not overtly technological, balancing between "look at me" and "I'm just a rock," how would you design it? You would likely create something that appeared mostly natural and could plausibly be dismissed as a comet or asteroid, yet had enough geometric regularity to attract the attention of those who look closely. You would need ambiguity, you would need the possibility of denial, you would want observers to argue about what they see, and that's exactly what we got. Radio astronomers, of course, found nothing. No clear periodic signals, no modulated carrier waves, no beacons transmitting through the electromagnetic spectrum to scream artificial origin. However, the absence of evidence is not evidence of absence, especially when we listen only in a narrow frequency range, when our radio telescopes can be directed at Atlas only during limited time windows, when the object moves so quickly that any signal will be heavily Doppler shifted and potentially unrecognizable. Thus, we are left with ambiguity, patterns that could be signals or mere rotations, chemistry that might be extraterrestrial or from a very different stellar cradle than ours, acceleration that could result from gas release or something else. Each collected data can be interpreted in various ways, sometimes even in a third way, and the choice between these interpretations requires either more information than we have or a bold decision in one direction or another. How does this relate to other interstellar objects we have discovered? What does historical experience tell us about objects that behave unusually? Let's turn to the shadow of Umalu and what it has taught us. The third part, the shadow of Umalu, October 19th, 2017. The Pan-STARRS telescope in Hawaii detected an object moving through the inner solar system on an impossible trajectory. Initially, astronomers speculated it was an asteroid or comet from our Kuiper belt, knocked off course by gravitational interaction. However, soon, As observations accumulated, the orbital calculations led to a disturbing conclusion. This object, which was soon named Umalu, meaning scout or messenger in Hawaiian, came from interstellar space. It was the first time in human history that we confirmed an object passing through our solar system originated from elsewhere. For the first time, we could confidently say we witnessed a visit from another star system, and it was strange. It accelerated slightly as it left the solar system, receiving a small but noticeable push that couldn't be explained by gravity alone. She had no comet tail, no gas emissions, and there were no visible signs of volatile ices that should have sublimated under the sun's heat. The shape of the object, judging by the changes in its brightness during rotation, indicated that it was extremely elongated, possibly 10 times longer than its width. Such geometry is virtually unknown among natural asteroids or comets. Some estimates even increased the elongation, suggesting a needle or cigar shape, which contradicted traditional formation mechanisms. The scientific community responded with numerous articles offering natural explanations. Perhaps it was a fragment of a planet torn apart by tidal forces. Perhaps it was made of unusual materials that did not show visible emissions. Maybe the acceleration was caused by sublimating hydrogen ice, too weak to be detected but sufficient to create thrust. The possibilities multiplied. Each explanation solved one problem, generating new ones. Each hypothesis required special conditions, suggesting situations that could be possible but were rare, convenient, yet unconfirmed. And then Abraham Loeb took the stage. Loeb, the chair of the astronomy department at Harvard, a scholar with an impressive list of publications and high status, publicly suggested that Oumuamua might be an artificial object. He suggested that it could be a solar sail, a thin reflective screen moving under radiation pressure, or part of a lost alien technology drifting in space, or, even more provocatively, an active probe from another civilization. The scientific community responded with fury. Loeb was accused of sensationalism, undermining the reputation of astronomy, and abandoning scientific rigor for publicity. The response to this phenomenon was so intense and emotional that it raised new questions about why the idea of extraterrestrial technology provokes such defensive reactions. 2 years later, in August 2019, another interstellar visitor arrived. This object, named Iberosov, behaved like a true comet. It emitted gas normally, had a visible tail, and its chemical composition matched that of comets from our solar system. The astronomical community breathed a sigh of relief. It seems they say interstellar objects are just like ours. Oumuamua was strange but ultimately explainable. Everything is fine. We could return to normal life if it weren't for one thing. Atlas won't let us go back to the familiar. In some ways, Atlas resembles Oumuamua more than Iberosov, as both objects exhibit non-standard acceleration, questioning simple gravitational models. Both possess chemical or physical properties that do not quite fit our classifications. They occupy the border space between a comet and a stone, being neither fully one nor the other. However, Atlas may be significantly larger than Oumuamua if size estimates are correct. It exhibits a strange emission of carbon dioxide that its predecessors did not. And the nickel signatures, extreme polarization, regular changes in brightness. All of this brings him into a new realm where our usual analogies cease to function. The most significant difference of Atlas from his brothers lies in the reaction he provoked. With Oumuamua, we were surprised, not knowing how to interpret what we saw, and ready to consider many possibilities. With Iberosov, we sighed with relief, eager to fit him into familiar categories. The scientific community had the impression that it had already decided what it wanted to believe before receiving all the evidence. After debates about Oumuamua, after accusations and counter-accusations, after a respected colleague was criticized for uncomfortable questions, many astronomers seemed to make a collective unconscious decision to play it safe, focusing on natural explanations to minimize anomalies. This is called a distortion. When you burn yourself touching a hot stove, you may become overly cautious with any stoves, even those that are clearly turned off. When the scientific community gets burned by public speculation about extraterrestrial technology, it can become overly skeptical of any evidence pointing in that direction, even if that evidence deserves serious consideration. The emotional memory of the debates about Oumuamua can influence how Atlas is interpreted now, creating a bias in favor of traditional explanations, which is as unscientific as the assumption that everything strange must be artificial. Loeb keeps track of anomalies, claiming that our interpretive frameworks are systematically biased against recognizing technological signatures. He points out that we have one confirmed example of a civilization that created objects for space travel. It's us. For decades, we have been sending probes beyond our solar system. The idea that another civilization could do the same is not wild speculation. This is the application of the principle of mediocrity, the concept that we are not unique, and what happened here likely happened elsewhere. If we believe that natural explanations are insufficient and resort to increasingly exotic conditions to support traditional interpretations, we may be ignoring the simplest explanation, which is only psychologically complex due to its consequences. Historical context matters here. Throughout the history of astronomy, we have encountered objects that seem strange, defying explanation, and sparking speculation about their unnatural origins. Pulsars, when first discovered, were jokingly called little green men because their regular radio pulses seemed artificially precise. Quasars challenged our understanding of how much energy could be released from a given volume of space. Fast radio bursts still lack a fully satisfactory explanation. In each case, we ultimately found natural mechanisms that could explain the observations, mechanisms that were often stranger and more interesting than artificial explanations. But here's the thing. Just because we found natural explanations for previous anomalies does not guarantee that every anomaly has a natural explanation. It's an induction error to assume that if X was true in the past, then X must be true in the future. At some point, if we ever encounter real evidence of extraterrestrial technology, it will look anomalous, it will contradict our initial models, and it will provoke exactly such debates. And if we have trained ourselves to always reject technological hypotheses, always finding some natural explanation, however far-fetched it may be, we might miss the most important discovery in human history, simply because we would prefer to be comfortably wrong than uncomfortably right. So what does this mean for Atlas? He spins in space on the edge between certainty and speculation, observed by instruments that see only fragments of truth, but never the whole picture. This brings us to perhaps the most troubling part of this story. The problem of absent data, images that should exist but have not been published, gaps in public records that may be harmless or otherwise. Let's consider what we do not see and why it may matter more than what we see. Part 4. The problem of missing data. Modern astronomy is a field saturated with data. We have telescopes in orbit, tools on Mars, observatories scattered across every continent. When something interesting enters the inner solar system, dozens of instruments can focus on it, capturing images in different wavelengths, creating a complete picture of what we are dealing with. This is the theory, at least. The practice, especially in the case of Atlas, looks significantly different. The European Space Agency released an animation created using the CASIS camera mounted on the ExoMars Trace Gas Orbiter. The CASIS, designed for capturing high-quality images of Mars's surface, was redirected to capture Atlas during its relatively close flyby of the planet. What did we obtain? A weak point moving against the stars, a blurred image barely distinguishable from noise confirming the existence of Atlas and its location predicted by orbital calculations, but providing almost no information about its physical properties. For an object that was believed to be tens of kilometers in size and within the visibility of a high-quality camera, the lack of details was disappointing. Either Atlas was much smaller than some estimates suggested, or it had a strangely dark color, or the camera was misaligned, or a combination of factors led to the least informative image. Then there was the Perseverance rover, NASA's flagship mission on Mars, which, equipped with navigation cameras, regularly scans the sky for dust devils and clouds, detected Atlas on October 4th as it appeared in the Martian sky. What did this image show? A beam of light corresponding to a moving object against a starry background, its direction and duration matching the predicted path of Atlas. Again, confirmation without revelation. We learned that Atlas is where it should be, moving as it should, but nothing about its true nature. These images were published, advertised, and written about in press releases and news articles. They said almost nothing, and perhaps that's okay. Perhaps these tools were simply not designed or positioned to provide higher quality data. But here is where the story gets strange. Other tools were supposed to capture images, higher quality images, and we did not see them. The Martian Reconnaissance Orbiter is equipped with a high-resolution imaging experiment capable of resolving objects on the surface of Mars down to 1 meter in size. When an interstellar object passes relatively close, one can expect high-resolution equipment to be deployed to capture images, many images, tracking the object over several orbits to create a comprehensive dataset. Where are these images? The MAVEN spacecraft studying the upper layers of Mars's atmosphere has optical instruments that could complement observations. Where is this data? The Mars Orbiter Odyssey, operational since 2001, has thermal cameras that could capture thermal signatures or assess the surface temperature of an object. Were these data published? Official explanations, if they are offered at all, refer to sensitivity limitations, scheduling conflicts, and tool restrictions. High resolution was developed for planetary surfaces, not for rapidly moving celestial bodies. MAVEN tools are optimized for atmospheric research, not for tracking asteroids. Data processing takes time, requires calibration, and needs verification before publication. By the way, at the beginning of the year 2025, the government shutdown occurred, which delayed many NASA operations and created a backlog of data processing tasks that are still being worked on. These explanations seem plausible, reasonable, and may very well be true, but they exist in a context where the lack of data creates fertile ground for alternative narratives. When people expect to find certain information and do not, when institutions with a history of meticulous documentation suddenly encounter gaps in their records, distrust fills the void. There is a long history of claims that space agencies have edited, delayed, or concealed anomalous images. The face on Mars, which turned out to be a mountain formed by erosion and shadows, was initially presented without sufficient explanation, leading to a generation's distrust in NASA's image publications. Many conspiracy theories claim that photographs from lunar missions, Martian rovers, and orbital research have been cleaned or retouched to hide evidence of structures, artifacts, or other anomalies. Most of these claims are unfounded, based on the search for patterns in noise, on perceiving design and randomness. However, the presence of mostly baseless claims does not mean that each of them is wrong, nor does it indicate that agencies are always transparent with difficult data. The European Space Agency operates with a 6-month embargo on most of its raw data. Images and measurements are collected, processed internally, used by scientific teams, and only then published in public archives. This is a standard practice designed to give researchers time to analyze data before it's released to the general public. It is scientifically justified and practically necessary. But this also means that there may be detailed images of Atlas at this moment that will not be available to the public until mid-2026. Images that could answer the questions we are currently discussing in informational ignorance. This creates a data vacuum effect, where the public knows that observations should exist but cannot access them. When the gap between what has been observed and what has been released becomes noticeable, narratives seek to fill this space. Some of these narratives are paranoid, some are conspiratorial, some suggest concealments, secret knowledge, and institutional deception, and some may actually be true, or at least partially true, because the absence of evidence is indeed evidence of absence, when you expected that this evidence would be presented. Consider the structures of stimuli that operate here. If Atlas is just a strange comet, the immediate release of all available data poses little risk and contributes to scientific understanding. If Atlas is something more undefined, which could be artificial, or has characteristics we cannot explain, then publishing this data creates issues. It attracts intense attention. It raises questions that the agency may not be prepared to answer. This may reveal the possibilities or limitations of our tools, which someone might prefer to keep secret. There is a risk of public panic or confusion if the conclusions are presented without proper context. None of this proves that something is being concealed, but it establishes that there are plausible motives for selective information publication and that the gap between the observed and what was reported is greater than can be explained by ordinary scientific caution. You are asked to trust that the institution studying the Atlas provides a complete picture, while simultaneously being told that a significant part of this picture will not be available for analysis for months or even years. This is not an easy request, especially considering the high stakes, which brings us to the question at the heart of this investigation. Why does it matter? If Atlas is a natural object, we will learn something interesting about interstellar chemistry and move on to the next. If it is artificial, it will be the biggest news in human history. But aside from these outcomes, what is really at stake in how we interpret anomalous objects? What are we really arguing about when we discuss whether Atlas is a comet or something else? Let's consider the very concept of faith and what it costs us. Part 5. Faith, Skepticism, and Bets. ask yourself a simple question. Why does it matter whether Atlas is just a comet or something more? What will change in your life, your plans, your understanding of your place in the universe if the answer turns out one way or another? If the Atlas is natural, if all these anomalies are explained by known chemistry and physics, we gain a rare window into the composition of another stellar system. We learn that planetary systems light years away can produce comets with different chemical signatures than ours, that star formation conditions vary more than we thought, and that the universe is diverse in ways we are just beginning to catalog. This is scientifically valuable, intellectually interesting. It's yet another data point in our expanding understanding of cosmic chemistry. We publish articles, refine models, move on to the next puzzle. If Atlas is artificial, if we are truly looking at evidence of extraterrestrial technology, everything changes. This is not an exaggeration. The confirmation that intelligence exists elsewhere, that civilizations can arise and endure long enough to send probes between stars, that we are not alone in the universe. This realization will be a turning point in human history, before and after. How we perceive our significance, our future, our responsibility to the cosmos will change in an instant. But these are pure outcomes, binary possibilities. A more complex question is what happens between these extremes in the realm of uncertainty, where we are now. Because right now, today, we do not know what an atlas is. We have data pointing in different directions. We have institutions making claims that we cannot verify ourselves. We have gaps in information that may be harmless or raise suspicions. And we, as a society, are asked to decide what to believe without access to all the facts. Here, psychological aspects come into play. How humanity reacts to a possible first contact, or even vague hints of it, shows who we are as a species. Do we approach the unknown with curiosity or fear? Do we demand transparency from our institutions or submit to their authority? Do we allow ourselves to consider uncomfortable possibilities or retreat into comforting certainties? The Atlas event, regardless of its final explanation, is a test of our civilizational maturity. There are also institutional interests. Space agencies depend on government funding and political support. Their budgets depend on maintaining trust, on being perceived as serious and scientific rather than speculative and sensational. If NASA or ESR announces they have found evidence of alien technology and turns out to be wrong, the reputational losses will be enormous. Funding may be cut, leadership may be replaced, future missions may be canceled. The structure of incentives pushes for caution, for confidence, to make only those claims that can be unequivocally defended. This is understandable. This is human. But this is also a bias that can cause us to miss or dismiss genuine anomalies, as acknowledging them comes with professional risk. Then there is the risk of confirmation bias, the tendency to interpret new data as confirmation of existing beliefs. If you want Atlas to be an alien zone, you will emphasize anomalies and downplay traditional explanations. Every strange data point becomes evidence for your hypothesis. Every gap in the public archive turns into proof of a conspiracy. You do not deceive and do not act irrationally on purpose. You are just a person filtering reality through the lens of your existing beliefs and desires. But there is also the opposite risk, the bias of rejection, the tendency to dismiss uncomfortable possibilities, regardless of evidence. If you are sure that Atlas should be a natural object, you will focus on traditional explanations and ignore anomalies. Each strange data point becomes a minor puzzle rather than a major mystery. Every gap in the records becomes a harmless delay rather than a suspicious concealment. You are not deceiving. You are simply protecting yourself from the discomfort of paradigm shifts, from the dizziness caused by challenging your fundamental beliefs about the universe. Both biases are traps. Both lead away from the truth. The question is whether you can hold multiple possibilities simultaneously, evaluating them based on data rather than preferences, updating one's beliefs as new information comes in, rather than clinging to initial positions regardless of what the universe shows. This touches on a deeper, philosophical question. Is belief in alien probes a modern myth, replacing gods and angels with technology, a projection of our hopes and fears onto space? Or is it a rational conclusion based on existing data? The application of the Bayesian approach suggests that, considering the age and size of the universe, the number of potentially habitable planets, and our own existence as proof of the possibility of intelligence arising, the chances of other civilizations and perhaps their messengers existing in the void are very high. The answer is not obvious. Both viewpoints have their arguments. Each can rely on facts and logic in its defense. One thing is clear. This question is of immense significance not only for our perception of Atlas, but also for understanding ourselves. Are we alone in the universe? If not, what does contact with others mean? If we are visited or observed, or simply passed by travelers from other worlds, what responsibility does this impose on us? These questions are not abstract philosophical exercises. They touch upon real life and have practical consequences for resource distribution, future planning, and understanding humanity's role in the cosmic drama. And here is the uncomfortable truth. We make these decisions, shape these beliefs, and grapple with these issues with incomplete information. A complete dataset exists somewhere. Images that could resolve ambiguities, spectroscopic data confirming or refuting hypotheses, observational records that would allow a clear view of Atlas, rather than through a veil of selective disclosure and institutional caution. But we do not have access to this information. We are asked to trust, to set aside doubts, and to accept that those who know more than we do are making the right decisions about what to share and what to conceal. Perhaps this is so. Perhaps the agencies studying the Atlas have excellent reasons for their communication strategies. Perhaps everything they do is scientifically justified and ethically acceptable. But the very structure of the situation, the asymmetry of information, and the gap between what is known and what is shared create conditions for distrust and speculation. When you treat the public like children unable to handle difficult truths, you shouldn't be surprised when they start to suspect that you are hiding something important. As a result, we remain in a state of uncertainty. A visitor from another star possesses traits that challenge our models, observed by instruments whose data is not fully accessible, and interpreted by institutions with complex motivations. The Atlas hangs in the sky, both literally and metaphorically, a question mark made of stone, or metal, or something entirely different, and we are asked to decide what we believe without the information needed for a rational choice. But Atlas is not the only strange phenomenon in space at the moment. Recent discoveries, fresh space news may provide context, contrast, or hints on how to interpret our interstellar guest. In the next act, we shift our attention to fresh news from space, to anomalies and events that may be interconnected or merely coincidental, or something entirely different. Sometimes, to understand one mystery, it is necessary to consider all the other mysteries surrounding it. Sometimes the pattern becomes visible only when you step back far enough to see the whole sky. Part 6. Black hole. Imagine the most massive object imaginable, a neutron star, twice as heavy, a galactic core, twice as static. Now imagine something with the mass of several suns, compressed into an area smaller than a city, distorting space-time so much that nothing, not even light, can escape its gravitational pull once it crosses the event horizon. You are imagining a black hole. Now release her into freedom. Detach her from any galaxy, any star system, any gravitational anchor. Let her wander in the void between the stars, a cosmic predator hunting in the dark. In the year 2025, astronomers confirmed the observation of what they call a runaway black hole, a stellar mass black hole, unbound to any obvious gravitational system, drifting through our galaxy like a ghost ship sailing between ports. This is a completely unexpected discovery. Black holes form when massive stars collapse, and the galactic dynamics that regulate the movement of stars can sometimes eject a black hole from its native cluster, sending it on a lonely journey through space. It is astonishing that such a black hole has been captured. Black holes, as is known, are invisible. They reveal themselves only through their gravitational effects on nearby objects or through radiation emitted by material falling into them. A runaway black hole without a companion star, without an accretion disk, and lacking convenient material for absorption and illumination is nearly undetectable by ordinary methods. The discovery was made possible through gravitational microlensing, a technique that uses Einstein's general theory of relativity. When a massive object passes between us and a background star, the gravity of this object distorts the light from the star, creating a temporary increase in brightness, followed by a decrease as its position changes. By carefully measuring these changes in brightness, astronomers can draw conclusions about the mass and speed of the passing object. In this case, the micro-lensing signature indicated a dark compact object with several solar masses moving through the galactic plane at a speed consistent with stellar remnants rather than a typical star. This confirmation was significant as it validated theoretical predictions and opened access to observations of a population of objects that should be widespread but are rarely seen. The model suggests that hundreds of millions of stellar mass black holes roam the Milky Way, remnants of ancient supernovae, most of which are completely invisible and undetectable unless they pass directly in front of a background light source we observe. We live in a galaxy filled with predatory gravitational wells that we cannot see. These are traps in the space-time continuum, ready to consume any careless body crossing their event horizons. And here arises an interesting question in the context of Atlas. Could a random black hole influence the trajectory of our interstellar visitors? Can gravitational interactions with such an object explain some of the orbital anomalies we observe? At first glance, this idea seems plausible. Black holes are powerful gravitational centers, and even an encounter with a distant black hole could deflect an object's path, potentially explaining the trajectory by which Atlas entered our solar system from the stellar vicinity where it could have originated. However, mathematically, this is not entirely justified. Gravitational interactions are well studied, and their behavior follows equations that we have tested with high precision. For a black hole to significantly alter Atlas's trajectory without capturing him or accelerating him to even greater speeds, an incredibly precise encounter would be required. Something like threading a needle through three-dimensional space at distances measured in light years. Theoretically, this is possible since physics does not prohibit it, but the likelihood of such an event is low. There are many ways in the universe that can alter trajectories without the involvement of random black holes. Nevertheless, symbolically, these two anomalies, existing simultaneously in our perception, have their resonating meaning: a black hole without a home and a comet without a clear origin, both wandering in space, both violating the familiar categories we like. They remind us that the galaxy is far more dynamic, chaotic, and filled with wandering dangers and mysteries than the orderly diagrams and textbooks suggest. We imagine space as mostly empty, with rare islands of matter and light. In reality, it is much more unsettling. The space is filled with invisible objects, massive bodies moving in darkness, and ancient remnants of stellar death circulating among the stars we can observe. The existence of wandering black holes also raises uncomfortable questions about what else might be out there in the vastness of space. If stellar remnants can be ejected from their systems, what about planetary remnants? What about objects that were never gravitationally bound? What about bodies that were intentionally directed along specific trajectories rather than by chance? Interstellar space sensors are almost completely unknown. We only see objects that emit or reflect light towards us. Everything else, including dark matter in a practical sense, remains invisible until it gets close enough to our instruments for detection. This is related to a broader theme that runs through our research. We discover that space is not a quiet, predictable environment as we thought. The smooth dynamics of the galaxy, which we assumed, where all objects move orderly around gravitational centers, is complicated by the presence of strange and unpredictable objects that do not follow established rules. If the scenario about black holes is incorrect, if it mistakes the number and nature of objects wandering between stars, what else might be wrong? It's interesting that events are unfolding right now. In the year 2025, we track an anomalous interstellar object in our solar system while simultaneously confirming the existence of wandering black holes in our galaxy. These discoveries are not necessarily related, but astronomy is an active field where new data constantly emerges. However, there is something in the coincidence of anomalies, in the cluster of strange observations over a short period, that makes pattern seekers ponder a possible connection that we do not notice. Correlation does not imply causation, but sometimes it may indicate deeper structures we have yet to recognize. And black holes are not the only cosmic issues requiring our attention. As we track objects moving through the galaxy, our own star has sustained damage affecting everything we try to observe. Let's focus on the sun and the hole that may hinder our view of the truth. Part 7. The colossal wound of the sun. The sun is not perfectly smooth. We imagine it as a perfect sphere filled with thermonuclear reactions and light, stable and predictable, like the cosmic engine that fuels our planetary system. However, the reality shown by solar telescopes is much harsher. The surface of the sun is full of convective cells and magnetic entanglements. Sunspots appear and disappear. Prominences rise thousands of kilometers into space, and sometimes the sun opens a wound. Coronal holes are exactly what they sound like. Gaps in the solar atmosphere where magnetic lines do not return to the surface, but instead rush into space. These are not holes in the physical sense, not voids where matter is absent, but areas where the plasma is cooler and less dense than the surrounding corona, making them dark in ultraviolet images. More importantly, it is in these areas that the solar wind travels unobstructed, accelerating to speeds of 800 kilometers per second, carrying charged particles and magnetic fields deep into the solar system. In October 2025, solar observatories recorded a massive coronal hole facing Earth, one of the largest in recent years. This hole occupied a significant part of the visible disk of the sun, representing a dark spot on the bright surface, like a cosmic wound that does not heal. Forecasts predicted that strong solar wind streams would reach Earth within a few days, potentially causing geomagnetic storms, disrupting satellite operations, creating auroras at unusually low latitudes, and generally making the electromagnetic environment near Earth more chaotic than usual. For most people, coronal holes are primarily interesting because they create magnificent auroras. Charged particles ejected by the sun interact with Earth's magnetic field and atmosphere, exciting atoms and molecules that emit light, painting the sky in green, red, and purple hues. This spectacle is truly impressive, one of the most beautiful natural phenomena, attracting photographers and tourists to high-latitude regions when strong solar activity is expected. However, for astronomers striving for precise observations of faint objects, solar storms become a real nightmare. The flow of charged particles interferes with radio observations, creating noise that masks weak signals. Fluctuations in the magnetic field affect the operation of spacecraft, which can degrade the quality of images from orbital telescopes. Even ground-based optical telescopes may suffer, as increased ionization in the upper atmosphere distorts the light passing through it. When the sun is active and coronal holes eject plasma towards Earth, our ability to see clearly in space decreases. Now let's pay attention to the timeline. Atlas reached perihelion, its closest point to the sun, on October 30th, 2025. At that moment, telescopes were supposed to gather the most detailed data as the object was brightest and closest for observation. It was precisely during this time that a massive coronal hole faced Earth, with solar wind reaching its peak and the electromagnetic environment being most disturbed. Coincidence? Almost certainly, solar activity follows its cycles, regardless of which asteroids or comets pass by. Coronal holes form according to magnetic dynamics that we do not fully control or predict. Coincidence is just bad luck, an unfavorable alignment of observant windows and sunny behavior, or is it not? Here we must be cautious with the narratives we create. It's easy to see patterns where there are none, to interpret coincidences as conspiracies, to imagine that the universe or some agency within it deliberately arranges events to obstruct observations. Most likely, this is not the case, but the effect remains, regardless of the reason. During that critical period when Atlas was in the best position for detailed study, our instruments operated in deteriorating conditions, overcoming solar noise to capture data, any barely perceptible signals, any subtle anomalies, any small details that could clarify the nature of the object. These observations were harder to conduct, easier to miss, and more likely to get lost in the noise. The metaphor here is irresistible. A hole in the sun, a wound in our star creates a smoke screen at the very moment we need clarity. This sounds like a thriller script, as if something was created to maximize uncertainty, and perhaps there is nothing special about it. Just a coincidence that seems significant because people tend to seek patterns in randomness. But it is also true that if you wanted to observe something while remaining unnoticed, if you intended to pass through a star system while staying in the shadows, it would be strategically wise to choose a moment of high solar activity. You would benefit from the degraded observation, from the noise that hides your signals, from the reduced clarity of the instruments tracking you. This is the problem of uncertainty. Once inside it, every set of data can be interpreted differently. A coronal hole is simply weather, solar dynamics following its patterns. Or a coronal hole is a smokescreen, an interference pattern favoring an object trying to remain unnoticed. Both explanations fit the facts. None of it can be definitively proven or disproven based on available information. and we find ourselves once again in the territory between knowledge and assumptions, while cosmic strangeness does not end at the holes in the sun. As we watched objects drift while our star ejected plasma into space, cosmologists began to rethink the ultimate fate of everything. Will the universe expand forever, or could it face collapse? Let's consider how beliefs about cosmic fate can influence our interpretation of modern anomalies. Part 8. The collapse clock starts ticking. The universe is expanding. Every galaxy we observe is moving away from every other galaxy, as space itself stretches like the surface of an inflating balloon. This was confirmed by observation since Edwin Hubble's work in the 1920s and refined over decades with increasingly precise measurements. Expansion accelerates, driven by what we call dark energy, a mysterious component of the universe acting like anti-gravity on cosmic scales, stretching space ever faster. According to the Standard Model, this expansion will continue forever. Galaxies will move away until they disappear beyond our cosmological horizon. Stars will fade one by one. The universe will become cold, dark, and empty as a result of heat death, which will take trillions and trillions of years. This was a commonly accepted view, a comfortable nightmare, if you will, a fate so distant and impersonal that it hardly registers as a threat. We have time, incomprehensible volumes of time, regardless of what happens to humanity, to Earth, to our corner of space. The universe itself will exist for billions of years. However, in the year 2025, some cosmological studies began to question this assumption. New analyses of dark energy behavior, subtle patterns in cosmic microwave background data, refined models of how the universe's expansion rate changed over time, all pointed to a possibility that was previously considered unlikely. What if dark energy is not constant? What if the universe weakens, changes its nature, or moves towards a phase transition that could lead to contraction instead of expansion? What if her fate lies not in thermodynamic death, but in a great collapse? A gravitational contraction that will ultimately gather everything back. Galaxies will collide, space will compress, matter and energy will be squeezed into a single point, reversing the process of the Big Bang. The scientific articles were cautious, filled with numerous caveats, emphasizing that the evidence was far from conclusive and the likelihood of eternal expansion still prevailed. However, the possibility of compression, once perceived as practically zero, was now assessed as small but not to be ignored, perhaps 1% or maybe 5%. This was enough for serious cosmologists to start considering this idea, conducting simulations and pondering what observational signs could confirm or refute the hypothesis. Why is this important for our Atlas research? Because cosmological narratives shape our perception of local events. When the ultimate fate of the universe seems certain, and we are confident in the cosmic storyline, anomalies fit into this stable structure. This comet is strange, but the universe is stable, so the oddities must be explainable within existing models. But when the cosmic narrative itself begins to lose stability, when the ending is rewritten, everything suddenly seems less certain. If we were wrong about the fate of the universe, what else might we be wrong about? If the very structure is changing, perhaps these anomalies deserve more attention than we have given them. There is also a psychological aspect to consider. Apocalyptic narratives and predictions of cosmic ends are typically intensified during periods of cultural anxiety or paradigm shifts. Medieval Europe was obsessed with prophecies of the end of the world during times of plague and social upheavals. The Cold War spawned numerous scenarios of nuclear winter and social collapse. Now, in an era of climate change, political instability, and rapid technological advancements, we see a renewed interest in scenarios of cosmic doom, both near and far. The narrative of the Great Collapse fits into this scheme. It is a cosmic reset button, an end that is also a beginning, a collapse that could lead to a new Big Bang in a new universe. This is psychologically satisfying, unlike thermodynamic death. Thermodynamic death is simply the victory of entropy. Everything slowly fades into oblivion. Collapse implies a goal, a cycle, the possibility that universes are born, die, and are reborn in an eternal pattern. His mythology is dressed in mathematical attire and appeals to something deep in human psychology that wants to believe existence has a structure and meaning beyond simple thermodynamics. Therefore, when articles appear suggesting the idea that the universe may collapse rather than expand endlessly, they present not just dry technical results. They offer a new narrative, a different way of thinking about cosmic destiny. This narrative prepares us to perceive current events through a specific lens. If the universe is indeed moving towards collapse, uniting everything that is scattered, perhaps interstellar visitors like Atlas are not random wanderers, but part of a broader plan, a cosmic choreography that we do not yet understand. This is undoubtedly speculative territory. The connection between cosmological models and interstellar objects is at best tenuous, but narratives do not have to be logically rigorous to have a psychological impact. When you believe that the universe is moving towards a fundamental transformation, you start to see signs of this transformation everywhere. Every anomaly becomes a harbinger. Every mystery becomes a clue. The frames of perception shift, and with them, your understanding of everything within those frames changes. And here is the unpleasant truth. Scientists are people. They are not immune to the influence of narrative. When broad culture focuses on endings and transformations, when cosmological models are in a state of uncertainty, when old certainties are questioned, this atmosphere influences how researchers interpret their data. What hypotheses do they consider plausible? What anomalies do they consider worthy of study? And which do they dismiss? Science is not a purely objective process, isolated from human psychology. This is human activity carried out by people with their biases and narrative aspirations, and these aspirations inevitably influence the work. Thus, articles about the Great Collapse, regardless of their ultimate truth, change the interpretive environment. They facilitate reflections on grand ideas, cosmic possibilities, and whether observed anomalies relate to larger patterns. They prove nothing about Atlas, but change the atmosphere in which it is interpreted. And sometimes the atmosphere matters as much as evidence. But let's shift the focus from cosmic fate to more pressing matters. While astronomers discuss the fate of the universe, something more grounded yet equally destructive is happening in our orbital space. Satellites fall regularly and unnoticed, and their fiery rain may conceal something important. Every day, somewhere above your head, a satellite dies. Not metaphorically, but literally. Metal, silicon, and solar panels heat up to thousands of degrees, piercing the Earth's atmosphere, evaporating, disintegrating, falling as microscopic particles or sometimes larger debris that survive and reach the surface. Recently, an astronomer from the Smithsonian Institution estimated that 1 or 2 Starlink satellites burn up or return to Earth daily. Not monthly, but daily. That's hundreds of objects a year from just one mega constellation, evaporating on descent. The reason is simple. Low Earth orbit is not empty. At heights of several hundred kilometers, a residual atmosphere still exists, sufficient to create a slight resistance for satellites. Over time, this resistance slows the satellites, lowering their orbit until they plunge into denser layers of the atmosphere and can no longer maintain altitude. Orbital decay is inevitable. Every launched satellite will eventually fall if it is not regularly lifted to maintain its orbit. For small satellites with limited fuel reserves, the operational lifespan may last only a few years before atmospheric drag leads to their final descent. Starlink, the SpaceX megasystem intended for global internet coverage, consists of thousands of low-orbit satellites. Plans include tens of thousands of satellites forming such a dense network that multiple satellites will be visible above the horizon from any point on Earth. This requires work in low orbits, where atmospheric resistance is significant, meaning satellites must be regularly replaced as they decay and burn up. Thus, we observe a daily rain of fire, a constant stream of dying equipment evaporating above our heads, mostly unnoticed, as individual events are too small and too common to make the news. But this creates certain problems for the observational environment. There is interference. Thousands of satellites reflect sunlight, hindering telescope observations and creating trails in astronomical images that need to be removed in digital format. This increases the number of false alarms, objects that briefly appear in the sky but turn out to be satellites or debris, not asteroids or comets. This complicates the already difficult task of tracking small objects in space, as it is necessary to distinguish between genuine celestial phenomena and the growing cloud of artificial equipment in Earth's orbit. For observers trying to study objects like Atlas, this matters. When analyzing faint objects, looking for subtle changes in brightness or trajectory, and trying to confirm whether the observation is real or an artifact, the presence of thousands of artificial objects in your field of view complicates everything. Every mysterious signal could be a companion. Every inexplicable glow might be a fragment catching sunlight at an unusual angle. The background noise increases, along with the complexity of extracting genuine signals from the noise. There is also a more speculative possibility worth considering. Could the spread of satellite activity serve as a cover for detecting or masking other anomalies? If you wanted to observe Earth without being clearly identified, merging with the thousands of existing artificial objects in near-Earth space would seem strategically wise. Every telescope that sees you could reasonably assume you are just another satellite, another fragment in orbit, just part of the growing interference that everyone has learned to filter out. Camouflage is not intentional on your part. It is created by the technological infrastructure of humanity, the collection of equipment that surrounds us. This is related to a broader theme of signal and noise, how increasing complexity makes clear perception difficult. The more satellites we launch, the harder astronomy becomes. As more space debris accumulates in orbit, it becomes harder to distinguish significant observations from insignificant ones. We create our own fog, surrounding ourselves with a technological haze that obscures the very cosmos we seek to explore, allowing everything that wishes to remain hidden, unclear, or unnoticed to benefit from this fog. The irony of the situation intensifies. We launch satellites to improve communication and observations in order to obtain better tools for studying the universe. However, by doing this, we worsen the environment in which these observations occur, making it harder to see faint objects, harder to track anomalies, and harder to understand whether what we discover is significant or just another piece of falling equipment reflecting sunlight while it burns. Progress creates its own obstacles. The better our technology becomes, the more it hinders itself. There is no easy solution. Satellites perform functions valued by people. Internet access, weather monitoring, communication infrastructure, all depend on the orbital grouping. Arguing about reducing the number of satellites means arguing against the opportunities and services that millions rely on. Therefore, the group will grow, chaos will increase, and conditions for observations will continue to worsen. This is the path we are on, and unless there is a significant change in politics or a technological breakthrough, this path will remain the same. This leads us to perhaps the most convoluted part of Atlas's story: the silence, the gaps in communication, the feeling that the institutions meant to share information are being held back. Why do agencies remain silent when strange things happen? What is the logic or fear behind selective disclosure of information? Let's consider silence itself and what it can tell us. Part 10. The silence before revelation. Silence is a kind of information. When you expect to hear something but don't, when institutions that usually communicate regularly suddenly fall silent, when the absence of statements becomes more noticeable than their presence, you receive a signal, even if it is a negative one. Silence surrounds Atlas, gaps between observations and announcements, meticulous checks of every public release, all convey something, even if we are unsure what exactly. Space agencies operate under constraints that most people do not even think about. Every image released to the public must be verified, calibrated, and confirmed. Every statement about observations must be accurate, justified, and unlikely to be refuted by future data. This is not censorship or a conspiracy, but ordinary caution of institutions that understand their reputation depends on the accuracy of information. If NASA announces a discovery that turns out to be the result of an instrumental error or misinterpretation, the consequences for their reputation can be serious and long-lasting. Therefore, they check, double-check, and wait until they are sure before announcing anything publicly. This creates a time gap, a delay between observation and announcement, usually measured in weeks or months. For routine observations, this is almost insignificant. So what if the press release about a distant galaxy comes out 6 months after the telescope took the picture? The galaxy isn't going anywhere. But for events requiring quick responses, for objects passing through our solar system on a schedule measured in days and weeks, this delay becomes significant. By the time the agency is ready to make a statement, the event has often already passed, the subject has moved on, and the public begins to wonder why it wasn't reported earlier. This pattern has been observed in several recent events. When new exoplanets are discovered through gravitational wave detection or transit methods, it often takes several months before the announcement is made. When radio telescopes capture interesting signals, the team conducts extensive checks before the information is made available to others. When orbital missions capture unusual images, they undergo processing and analysis that can take a year or more before publication. This is a standard procedure, not specific to Atlas or any particular mission, but standard practice feels different when the observation could be exceptional, when the delay affects data that could answer fundamental questions about our place in the universe. When the gap between observation and reporting creates space for speculation and alternative narratives, familiar caution begins to be perceived differently. It begins to look like deliberate concealment, like information control, like an institution's decision about what the public can know and when. Here, institutional interests create problems. Agencies want to control their narratives. They want to make announcements at their own pace, in their own words and context. Leaks are bad. Premature publications are bad. Speculation before verification is bad. All of this seems logical from the agency's perspective, but from the public's point of view, it looks like secrecy. It appears as if decisions are made behind closed doors about what information is suitable for the general audience. And this appearance, regardless of whether it reflects reality, undermines trust. There are historical examples where agencies delayed or initially concealed anomalous findings. The famous image of the face on Mars, captured by the Viking spacecraft in 1976, was initially presented in a press release that emphasized its artificial appearance. Later publications provided context explaining how lighting and resolution affected interpretation. The WOW signal, recorded in 1977 by CT researchers, was not publicly discussed for a long time, despite being one of the most intriguing radio observations. Then the beginning of the eclipse of Tabby's star, which some speculated might be evidence of an extraterrestrial megastructure, became known to scientists long before it was made public. In each of these cases, there were rational explanations for the delay. Scientists wanted to eliminate equipment errors, gather more data, and avoided making claims they couldn't defend. However, the effect remained the same. The public learned about potentially significant observations only after some time through channels that resembled PR management more than transparent scientific communication. Each of these events reinforced the feeling that scientific institutions control information, deciding which questions are permissible for public discussion and which should remain in private conversations among certified experts. Let's apply this scheme to the Atlas. The object was discovered in July. It is now the end of October. We have seen only a few images, mostly showing dull dots or lines. We read press releases emphasizing the natural origin of the comet, downplaying anomalies, reassuring us that everything is normal and expected. We did not see high-quality images from the devices that were supposed to capture them. We were not provided with raw spectroscopic data that would allow independent researchers to confirm the chemical claims. We are asked to trust that the institution studying the Atlas provides us with all the important information, while their history suggests that this is not always the case. This creates what can be called a window of silence, a gap between observation and revelation where narrative control occurs. During this period, the agency controls history, deciding what will be emphasized and what will be hidden in technical applications, shaping the narrative and language that defines public interpretation. And all this happens behind closed doors, in internal meetings and during the review process, inaccessible to the public. By the time we receive the official version, the narrative is already formed, the interpretation defined, and the acceptable range of speculation established. Is this a conspiracy? Not in the sense of malicious concealment, but rather information control, narrative management, self-defense of the institution. This creates conditions where conspiracy theories thrive, because when people realize they are not receiving complete information, they fill in the gaps with their own narratives, often more dramatic and less plausible than the truth, if it were simply shared openly. The Atlas is at the center of several strange signals, many cosmic anomalies that may be either independent or interconnected. Wandering black holes in the galaxy. Holes in the sun disrupt observations, cosmological models are in a state of uncertainty, satellites fall from the sky like rain. Each of these phenomena can be an independent event or part of a larger picture that we cannot see because the data is scattered, publications are delayed, and the narrative is fragmented due to the caution of institutions and communication strategies. It is known that at this moment, an object from another star system is passing through our system, possessing properties that challenge our models. The scientists studying it are cautious about what they share and when. Silence may mean nothing, or it may mean everything. We won't know until the window closes, until the data is finally published, until we can see for ourselves what Atlas really is. Until then, we are left with gaps and guesses as we watch the sky and wonder what is seen, but not reported. Speaking of the sky, let's pay attention to the calendar. While all these oddities unfold, celestial events follow a schedule set by orbital mechanics and cosmic time. These events, these spectacles can distract or present opportunities. They can hide what we need to see or reveal what was concealed. In any case, they will inevitably happen. Mark your calendars. The show is about to begin. Part 11. The cold moon rises on December 4th. The moon has many names inherited from cultures that tracked its phases like a calendar and clock. The full cold moon rises on December 4th, 2025, a name given by colonial Americans in accordance with the traditions of indigenous peoples who associated this full moon with the onset of deep winter, cold nights, and frozen ground, with a year approaching its darkest point before the solstice, ultimately promising the return of light. There is something primal about full moons. They have influenced human behavior throughout history, marking time for hunting, sowing, rituals, and celebrations. Modern people like to think that we have overcome such influences, that electric lamps and digital calendars have freed us from the moon's grip. Yet emergency rooms in hospitals still report increased activity during full moons. The police note changes in call patterns. Sleep studies show measurable effects on human circadian rhythms, even when subjects cannot see the moon. We are still animals, still subject to the ancient rhythms in which our ancestors evolved, even if we pretend otherwise. The cold moon will be visible worldwide, weather permitting, rising in the east as the sun sets in the west, reaching its highest point around midnight, illuminating the landscape with its special colorless light, bright enough to read by, but not bright enough to distinguish colors. The light at the boundary between day and night makes the familiar world strange, and the strange world visible. From an astronomical point of view, this full moon is unremarkable. It is not a supermoon, not approaching Earth, and does not stand out in brightness. It is just the moon completing another cycle, reflecting sunlight towards Earth. However, symbolically, culturally, and psychologically, this event holds significance. People will go out to admire the moon. Photographers will capture its rise over landscapes and cities. Social networks will be filled with images of the moon, each slightly different, each trying to convey an indescribable feeling. Standing under this light and feeling both insignificant, connected to everything, and ancient. Now let's imagine another perspective. What if anomalies like Atlas occur when public attention is focused elsewhere, intentionally or accidentally? The full moon is a natural spotlight, a celestial event that attracts millions of gazes. When people look at the moon, they see nothing else. When telescopes are aimed at the moon, or when its brightness drowns out faint objects, they do not track anomalies in other parts of the sky. The moon essentially creates a blind spot, a moment of collective attention that can obscure other events happening simultaneously. This does not mean that there is some cosmic conspiracy where alien visitors coordinate their appearances with the phases of the moon. That is absurd. However, it is worth noting that when human attention is focused in one direction, opportunities arise in others. Illusionists understand this principle. The art of distraction is the foundation of their skill. If the audience looks at the right hand, they do not notice what the left is doing. If the audience looks at the moon, they miss what is moving in the dark sky behind it. The cold moon also carries symbolic meaning that influences how we interpret events around its appearance. Cold is associated with completion, hibernation, the end of a cycle. December is a time when everything stops, when growth ceases, when the world turns inward. If strange events occur at this time, if revelations or discoveries happen in early December, they will be interpreted through the lens of this symbolic meaning, as an ending rather than a beginning, as a closure rather than an opening. The narrative frame changes depending on the time when something becomes known, even if this coincidence is purely accidental. Or maybe it really is a coincidence. Perhaps the phases of the moon and interstellar visits have nothing in common. Perhaps the cold moon is just a moon, and Atlas simply passes by, with any connection between them being an attempt to see patterns in randomness. But a human is a creature that creates stories. We cannot help but notice narratives in events, connections in coincidences, meaning in time. The moon rises, a visitor passes by, and somewhere in this intersection, we create a story that makes sense to us, even if it doesn't make sense to the universe. It's important to pay attention to what you pay attention to. When the cold moon rises and your gaze turns to the sky, ask yourself what else is happening. What other objects are moving in space? What data is published or hidden? What announcements are made or postponed? The moon is beautiful, worth observing, photographing, and noting. But do not let its beauty overshadow everything else the sky contains. Sometimes a spectacle is just a spectacle, and sometimes it hides something you might notice. Speaking of spectacle, the cold moon is just a prelude. Soon, the supermoon will arrive, larger and brighter, undoubtedly taking over headlines and social media. Let's consider how the grandest lunar show of 2025 might influence what we see and what we miss. Part 12. The supermoon of 2025. In early November, the supermoon sounds dramatic, like from comics or disaster movies. In reality, it's much subtler, yet still truly impressive. A supermoon occurs when a full moon coincides with perigee, the point in the moon's elliptical orbit where it comes closest to Earth. The moon's orbit is not circular but elliptical, meaning that sometimes the moon is about 50,000 kilometers farther from the Earth than at other times. When a full moon occurs at perigee, the moon appears about 14% larger and 30% brighter than when it is at apogee, its farthest point. It is quite noticeable if you pay attention, especially when the supermoon rises close to the horizon, where atmospheric effects can create an optical illusion, making it appear even larger. The biggest supermoon of the year 2025 will occur in early November, either on the 3rd or 4th, depending on the exact moment of perigee and full illumination. For ordinary observers, this difference does not matter. It is important that for several nights the moon will dominate the night sky, bright enough to cast strong shadows and beautiful enough to stop people in their tracks, becoming a cultural event rather than just an astronomical phenomenon. And here it becomes especially interesting from our point of view. Supermoons generate massive public interest. It is accessible astronomy, requiring no equipment except for eyes and curiosity. News agencies cover them. The weather forecast mentions them. Social media is filled with photographs of the supermoon taken from various locations and angles. For several nights, millions of people who usually never think about celestial mechanics become enthusiasts of moon observation, stepping outside to look up, sharing what they see, participating in a collective astronomical experience. It's wonderful. Everything that sparks interest in space makes people look up in wonder, connecting them with the cosmos beyond their immediate concerns. This is a positive contribution to civilization, but it also represents a huge diversion of attention. When everyone is looking at the moon, when telescopes study its brightness, and cultural discourse is filled with images of supermoons, other events may go almost unnoticed. The closest approach of Atlas to Earth will occur at the end of October, just before November, when a supermoon will be observed. This coincidence means that at the moment when Atlas will be passing the most noticeable part of its trajectory, public attention will be focused on the lunar spectacle. Professional astronomers will, of course, continue to monitor Atlas. They are not distracted by the beautiful moons, but public attention, media coverage, and broader discussions about what is happening in space shift towards a more accessible and spectacular event. Atlas becomes background noise, if mentioned at all, overshadowed by the mass appeal of the supermoon. There is a historical pattern worth noting. Important announcements are sometimes made when public attention is focused elsewhere. States announce unpopular decisions on Friday afternoons before holiday weekends. Corporations publish negative financial news after markets close. This is not necessarily a conspiracy. It's just strategic communication, timing that minimizes negative attention, or allows the message to be perceived without immediate scrutiny. Can the same principles be applied to cosmic anomalies? Can the timelines of revealing or concealing information about major celestial events be part of a deliberate strategy to manage public reaction? Perhaps. Or maybe it's just a coincidence, the result of orbital mechanics and observational windows, unrelated to communication strategy, but the effect remains. When the supermoon dominates the cultural discourse about space, anomalies like Atlas fade into the background. Questions that could have been voiced loudly in a calmer news environment are asked quietly, or not at all, drowned out by the excitement around the supermoons. And here is the psychological aspect. Supermoons strangely calm. They are predictable, expected, part of the regular rhythm of celestial mechanics. They remind us that some aspects of the universe are stable, that orbital dynamics obey understandable laws, and that we can predict and prepare for these events with absolute accuracy. In an era of cosmic uncertainty, when scientific discourse discusses interstellar guests, runaway black holes, and scenarios of cosmological catastrophe, the supermoon offers solace. It says, "Look, the universe still functions as you studied in school. The moon still orbits the Earth. Perigee and apogee occur on schedule. Not everything is strange." This is a comfort, a return to the familiar, perhaps exactly what people need psychologically. Or perhaps this is what prevents them from coping with truly strange events. When you are offered comfort, when the spectacle becomes an easy focal point, there is a temptation to accept it and ignore the more complex, troubling questions that lie beyond attention. The supermoon is beautiful, but beauty can become a trap, holding your gaze in one direction while other paths remain unexplored. So when the supermoon rises in November, filling the sky with its enlarged, bright disk, remember to look around. Check what else is visible. Ask questions about the data that is published or hidden. Note whether announcements happen during the supermoon or are strategically postponed until after the spectacle passes. The moon deserves your attention, but should not monopolize it. The sky is larger than the brightest object in it, and sometimes the most important events happen in the dark corners we would rather not explore. Speaking of events passing through the darkness, the supermoon is not the only celestial show scheduled for the coming months. Meteor showers are approaching, annual events that ignite the sky with fire and have their ways of drawing attention, perhaps hiding what we should notice. Let's pay attention to the southern Taurids and what happens when the sky fills with glowing trails. Part 13. Lights in the Sky. Southern Taurids. Every year in early November, Earth's orbit passes through a stream of debris left by Comet Encke, a short-period comet that enters the inner solar system every 3.5 years. The debris forms a river of particles distributed along the comet's orbital path, and when Earth crosses this river, the particles crash into our atmosphere at about 30 kilometers per second. Friction heats them to a bright red state. They evaporate in sparkling trails. We call it a meteor shower, specifically the southern Taurids, because the meteors seem to emit light from the constellation Taurus. The southern Taurids are not the most spectacular meteor shower. Peak rates usually amount to only 5 to 10 meteors per hour, which is modest compared to showers like the Perseids or Geminids that can produce dozens or even hundreds of meteors per hour at their peak. But Taurid meteors are renowned among meteor enthusiasts for their bright fireballs, and usually bright meteors that can momentarily overshadow even the brightest stars, sometimes leaving lasting trails of ionized gas that remain for several seconds after the meteor itself disappears. Rain is active from the end of September to the end of November, with a peak activity period usually occurring in early November, coinciding with the supermoon window we just discussed. Thus, during the same period when the moon is extraordinarily bright and public attention is directed to the sky is also regularly crossed by meteors, natural fireworks that enhance the overall feeling that many events are happening above our heads. On one hand, it is a pure coincidence. Earth's orbit is fixed. The debris stream of Comet Encke is in its place. The perigee of the moon occurs when it occurs. These phenomena are independent and determined by the laws of gravity, which are beyond human observation or interpretation. A coincidence in time is simply the universe busy with many processes at once. From another perspective, this coincidence creates noise. When you try to track specific objects in space, searching for anomalies or unusual trajectories, a sky filled with meteors complicates the task. Each light streak must be identified. Is it a Taurid meteor, a satellite, space debris, or something else? The more natural phenomena occur, the harder it is to distinguish between signal and noise, genuine anomaly and expected event. And here is a question for contemplation. Can fragments of interstellar objects be mistakenly classified as meteors? Comet Atlas is ejecting substances, shedding material as it passes through the solar system. This material forms a tail, a cloud of particles following the comet's trajectory. If the Earth accidentally passes through this stream of particles, if pieces of interstellar matter enter our atmosphere, will we recognize them as distinct from the annual meteor showers we expect? Or will we assume that they are just part of the Taurids? Just another piece of debris from Comet Encke, and shall we not delve further? Chemical analysis should show the difference. Meteor spectroscopy can determine composition. The material of an interstellar object should display chemical signatures distinct from solar system comets. But this assumes that someone will capture the spectrum of a specific meteor, that the observation will occur during those brief seconds while the meteor is visible, and that someone will notice something unusual enough to warrant detailed analysis. For the overwhelming majority of meteors, we only see a trail, perhaps photograph it, and move on. Detailed spectroscopy is conducted only for the most interesting or well-observed cases. This creates a blending effect. High meteor activity provides cover, a backdrop for expected events that can hide the unexpected. If you wanted to study Earth without being clearly identified, dropping material that could enter Earth's atmosphere would be strategically justified if coinciding with a major meteor shower. Your trash mixes with expected trash, your signals are lost among expected signals, and human observers, seeing what they expect to see, classify everything as part of a known phenomenon without delving into details. Again, this is just a hypothesis. There is no evidence that the fragments of Atlas enter the Earth's atmosphere. There is no confirmation that anything unusual is hidden among the torids, but the structural possibility exists. Theoretical window where misidentification can occur is noteworthy, as it affects how confidently we can claim to know what we observe. There are also simple facts. Meteor showers draw eyes upward. Like a supermoon, like any celestial spectacle, they focus attention in specific directions at particular moments. When people are outside watching fiery orbs, they interact with the sky in a way they usually do not. They notice details, point them out, take photos, but the main focus is on the meteors, the anticipated show. Other objects moving across the sky may be visible, but are perceived as a backdrop for the main event. The torrid zone also has its mythology and is discussed in astronomical circles. Some researchers have suggested that the torrid complex, a wide stream of debris, associated with a comet NK, may contain larger fragments, rocks the size of a kilometer, which pose a potential threat to Earth. These statements remain controversial and have not gained widespread support, but they give the event an underlying sense of threat despite its beauty. Watching the torrid meteors, you see small particles that pose no danger, but a question may arise in the depths of your mind if there is something more hidden in the same stream of debris, possibly on a collision course. Atlas is not related to the torrid complex. His origin is interstellar, completely unrelated to the comet NK. But the psychological association, the connection between celestial objects and potential threat, creates a context in which anomalous objects are perceived as dangerous. Torids remind us that space harbors dangers. An atlas arriving from interstellar space with unusual properties is categorized as a threat, even though it poses no collision risk. These narratives intertwine not because they are actually connected, but because they evoke similar psychological responses. Therefore, when the southern torrid zones reach their peak in early November, when the sky is filled with light trails and fireballs, pay attention not only to meteors, but also to anything else that might move. Notice if unusual objects are reported and denied. Ask yourself whether this blend of patterns is innocent or convenient. The torrid ones are worth watching. This is a true natural wonder, a reminder that we live in a dynamic system where matter is constantly moving. But do not let the expected show blind you to the unexpected events happening in other parts of the sky. And the torrid zones are just the beginning. Ahead of us are meteor showers, a cascade of celestial fireworks that will illuminate the sky in November and December. Let's consider how this concentration of spectacles can shape what we see and what remains hidden between the trails of light. Part 14. Leonids, Geminids, and Ursid meteor showers. The sky at the end of 2025 will be filled not only with Atlas, supermoons, and coronal holes, but also with a regular program of meteor showers, 3 main shows appearing in rapid succession, like a coordinated performance planned by the universe itself. The Leonids appear on the 17th and 18th of November, formed from the debris of the Tempel-Tuttle comet, meteors that seem to emanate from the constellation Leo. The Leonids are known for sometimes causing meteor storms, when thousands of meteors can be seen illuminating the sky in an hour. However, such storms occur only in certain years when the Earth passes through particularly dense sections of debris flow. The year 2025 will not be stormy. Leonids will be moderate, possibly 10 to 15 meteors per hour at peak, visible in the pre-dawn hours when Leo is at zenith. Then the Geminids will arrive on the 13th and 14th of December, usually considered the most reliable and impressive meteor shower of the year. The Geminids are unusual in that they originate not from a comet, but from asteroid 3200 Phaethon. This may be a long-extinct comet that has shed all its volatile substances and now consists only of a rocky core. The Geminids can produce up to 120 meteors per hour during peak activity, with bright, multicolored trails visible from anywhere on Earth, weather permitting. This reliable spectacle draws media attention and prompts people to go outside even in the December cold. Finally, the Ursid meteor shower on December 21st and 22nd, originating from the constellation Ursa Minor, formed by the debris of Comet Tuttle. Ursids are usually rare, perhaps 5 to 10 meteors per hour, suffering from bad timing, peaking around the winter solstice when nights are longest in the northern hemisphere, but the weather is often poor. They are the quiet concluding act of the meteor calendar year, less impressive than the Geminids, but still a regular part of the December sky. 3 major streams over 5 weeks, coinciding with Atlas's passage through the inner solar system, coinciding with a supermoon, coinciding with increased solar activity due to a coronal hole. If you were planning a period of maximum celestial activity, maximum interest in the sky, you couldn't have scripted it better. The universe gifted a magnificent autumn and the beginning of winter, a season of cosmic spectacles that will captivate astronomers and casual observers for months. And here arises the question of patterns. When meteor showers accumulate and the sky is regularly crossed by expected phenomena, the observational environment becomes more complex. Each unknown object must be distinguished from the known background. Every anomalous observation competes for attention with impressive but explainable events. Meteors are beautiful, worth observing, scientifically interesting in themselves. But from the perspective of tracking other objects, they also create noise, a baseline level of activity that other signals must surpass to be noticed. Good interstellar fragments, twilight clouds tracking the path of Atlas, particles ejected during its passage through our solar system. Could some of these phenomena coincide with regular meteor showers? Perhaps material from another star system is currently entering Earth's atmosphere, burning alongside the Leonids or Geminids meteors, remaining misclassified or simply unnoticed, because we expect to see meteors during these periods and see only what we expect. The chemical composition could reveal the truth if we looked closer, but we do not record detailed spectra of every meteor. We do not analyze every trace. The vast majority of meteors are observed visually, perhaps photographed, and that is all. Only a tiny fraction receives careful scientific study, capable of revealing unusual composition. So, if interstellar material mixes with solar system material, if anomalous particles hide among the expected, the chances of their detection are slim unless something is distinctly different, spectacularly strange, or impossible to classify. Here, the human factor is also present. When celestial phenomena become part of the calendar, when they are expected and anticipated, they become part of the background of reality. The Geminids occur every December, the Leonids every November. These are facts, regular events, predictable like the seasons. This is not a mystery or an anomaly. It is the cosmic infrastructure, the regular rhythm of Earth's journey around the sun, passing through streams of debris left by various comets and asteroids. This normalization is useful. It allows predicting and preparing for events, planning observations and public events, turning chaotic cosmic phenomena into understandable patterns. But it also creates blind spots. When something becomes the norm, we stop questioning it, stop looking at it with fresh eyes, classify it, archive it, and move on. And if something truly unusual is hidden in the normalized pattern, we might miss it because we have taught ourselves not to look too closely at events that we think we understand. The folding of these streams around the passage of Atlas may be a simple coincidence. Orbital mechanics does not care about our narratives. Earth's path through various debris streams is determined by the laws of gravity, which operate independently of the interstellar objects passing nearby at the same time. There is no reason to believe that the timing of coincidence matters, except that time creates context. When important news appears during distractions, it receives less attention. When significant events occur while the public is focused on something else, they can be missed or undervalued. The same can happen on a cosmic scale. When the sky is full of expected spectacles, meteor showers, supermoons, and other regular phenomena capture all attention, anomalies may pass by with less notice than they would in calmer times. This is a natural consequence of limited attention. In the world, there are only a certain number of hours at night, just a few telescopes pointed at the sky, and limited capabilities for data analysis. When many events occur, not everything receives equal attention. Priorities are set, resources are allocated, and some potentially important things may be pushed to the background simply because they compete with more relevant or spectacular events. So when the Leonids, Geminids, and Arids illuminate the night sky, remember that you are witnessing a curated show, not by a person, but by the limits of attention and observation. What you see is the brightest, most obvious, and anticipated. What you do not see may be more important, hidden in the dark spaces between meteors moving across the sky while your eyes follow their trails. This brings us to the last question we discussed throughout our research. Are all these cosmic events, moons, meteors, holes, and anomalies, just coincidences? Just the universe occupied with many unrelated tasks at once? Or is there something more that we do not notice because we are too close to see it clearly? Let's step back and consider the calendar, questioning whether we live in anticipation of something yet unidentified. Part 15. The calendar or countdown. Look at what we have gathered. An interstellar object with anomalous properties passing through our solar system. A wandering black hole in our galaxy. A massive coronal hole disrupting solar observations. Cosmological studies suggesting that the universe may be contracting rather than expanding infinitely. Satellites falling daily and creating observational noise. Supermoon attracting public attention. 3 major meteor showers grouped over 5 weeks. The cold moon rises, embodying completion and closure. Each of these events can be explained, they are natural, expected, or at least not surprising. The universe is vast and busy. Strange things happen regularly. Finding several strange events occurring simultaneously should not surprise us. The sample size is enormous. The number of potentially interesting cosmic events is great. Some overlap is inevitable, but there is something in this merging that troubles the mind-seeking patterns. These are not just random events scattered over time. They are grouped, concentrated in a narrow time frame from the end of October to December 2025. And they all, in one way or another, affect our ability to observe clearly or our attention as observers. A coronal hole worsens the performance of instruments. A supermoon attracts attention. Meteor showers create a backdrop. Satellites add clutter. The atlas moves through all this, unclear and anomalous, observed but not distinctly, questioned but without answers. So, let us consider 3 interpretive frameworks, 3 ways to understand what we observe. The first is pure coincidence. The universe does not care about human perception or interpretation. These events are independent phenomena that coincide by chance, as random distributions do. Clusters emerge from randomness. Coincidences happen. Seeing a pattern here is merely an illusion, a human tendency to perceive meaningful connections in meaningless noise. This is the safest interpretation, requiring no special evidence or exotic hypotheses. It is likely true. The second frame is narrative disguise. This is not a conspiracy or coordination, but a structural state in which true anomalies benefit from occurring during periods of high noise and distraction. If Atlas is something unusual that could attract attention during more peaceful times, then its appearance in the season of spectacles provides a natural cover. Not because someone planned it that way, but because the loaded observational environment makes it difficult to concentrate, confirms, and simplifies the possibility of postponing analysis for later. Within this interpretation, the timing of emergence does not necessarily need to be intentional to have consequences. The effect exists independently of intentions. The third frame is cosmic choreography. This is the most speculative and difficult to defend approach, but it is worth voicing. What if these events are connected on a level we do not recognize? What if Atlas is part of something greater, a phenomenon or process that simultaneously affects several aspects of the cosmic environment? We assume these were independent variables, separate events occurring in parallel. But what if they are somehow connected? What if the wandering of black holes, interstellar visitors, solar activity, and even the distribution of meteor showers are connected through mechanisms we have yet to uncover? Within this framework, we do not see a coincidence. We observe a pattern whose logic remains hidden because we lack the theoretical basis to recognize it. Each frame has its strengths and weaknesses. The matching frame is economical but may ignore genuine anomalies. The camouflage frame recognizes structural effects without requiring intentions, but it may excessively interpret noise. The choreography frame is intellectually engaging but demands evidence that we do not have, and likely will not. Choosing between them requires evaluating not only the data, but also philosophical beliefs about how the universe is structured, whether it contains hidden patterns, and if coincidence always remains just coincidence. It is clear that the heavenly calendar of the year 2025 presents an unusually rich collection of events. Is this wealth accidental or significant? Does it aid in discovery or hinder it? Are we experiencing cosmic routine or something more important? These questions cannot be answered definitively based on the available information. We remain in a state of uncertainty, looking at the sky, watching the schedule, wondering if the calendar counts time or counts down to something. And here comes the last uncomfortable thought. Perhaps the question itself is the essence. Perhaps what matters more is not whether Atlas is natural or artificial, whether the timing is random or planned, whether we are witnessing something unusual or simply misinterpreting the ordinary through the lens of our hopes and fears. Perhaps the main thing is that we ask these questions, that we look up, that we struggle with uncertainty rather than retreating into complete certainty. The narrative of Atlas, the story we create about what he is and what it means, says as much about us as it does about the object itself. He shows how we deal with ambiguity, whether we rush to conclusions or remain in a state of ignorance, whether we trust institutions or doubt them, whether we are ready to accept uncomfortable possibilities or need the universe to behave in an expected manner for our psychological comfort. So look up, watch the cold moon rise, count the meteors as they streak by. Notice the brightness of the supermoon and the darkness around it. Watch Atlas as he traverses our solar system and vanishes back into interstellar emptiness, but also look within yourself. Notice what you want to believe and why. Observe what causes you discomfort and what that discomfort protects you from. Pay attention to the stories you tell yourself about what happens in the sky and recognize them as narratives, human constructs imposed on phenomena that exist independently of our interpretations. The calendar continues. A countdown, if there is one, goes on its own course. According to schedules we do not control, events will unfold, data will eventually be published or remain hidden, questions will be answered or transformed into new questions, and we will be here, observing, wondering, creating narratives, because that is what people do when faced with a mystery. Who created this schedule? A cluster of cosmic events in certain months. Did someone write it? Or is the question itself a category error, an attempt to impose authorship on processes that simply exist? The universe does not write, does not plan. It evolves according to laws that we partially understand, creating patterns that sometimes appear intentional, but may just be the inevitable result of complexity developing over vast timescales. Or perhaps some patterns are indeed designed. Some time frames are intentional, and some objects passing through our sky carry intention rather than mere inertia. We do not know. We cannot know until we can observe and measure more. But we can remain open to the possibility, avoiding the trap of certainty in any direction. If you believe in the narrative that Atlas is just a comet, perhaps you are right. Perhaps you are missing the most important discovery in human history because you preferred comfort over discomfort, certainty over uncertainty, the known over the truly alien. If you believe the tale that Atlas represents something greater, you might be right. But it is also possible that you are simply looking for patterns in the random, seeing design in chaos, building complex theories to explain data that has simpler explanations. The only intellectually honest position is doubt combined with attention. Doubt that we know enough for final conclusions, and attention to what the universe shows us, even when it is uncomfortable or uncertain. The sky does not care what we believe. It simply exists. We, temporary observers with limited tools and biased interpretations, do our best to interpret its messages written in light and gravity, as well as the movement of objects at unimaginable distances. Look up, but also ask questions about who made the schedule, if anyone made it at all. Inquire what you are overlooking while observing what is most noticeable. Ask whether the narrative you accepted is the one you chose or the one imposed on you. The cosmos is vast, strange, and indifferent to human stories, but we are beings who love to tell stories. and the stories we tell about what is above us shape our understanding of who we are. Therefore, tell these stories carefully, subject them to strict analysis, and remember that the truest answer to cosmic mysteries may remain, at least for now, simple. We do not know, but we observe, and this observation itself is the beginning of wisdom.